If you want to switch your camera off, you might have a better bandwidth. It's up to you. Okay, all to you now, Harry.
Yeah.
Good luck.
Right, we're okay. I can nearly see the screen. Excuse me. Good afternoon again, ladies and gentlemen. If you recall, in the previous presentation, we actually recovered uranium from an ore body. We converted and purified the uranium using largely a ion exchange process. We precipitated the uranium out of solution once we'd removed it from the ion exchange material. Excuse me. We precipitated it out of solution. We filtered that solid uranium, the yellow cake, filtered it away from the filtrate, dried that solid material. We then placed it into 45-gallon, 210-litre drums, mild steel drums, and the refinery, let's assume we're talking about a refinery in Canada, would then send it to the mining company would then send it to the refinery, someone like BNFL that was at Preston. Now, in all fairness, you may ask yourself, why am I going to tell you about an operation that was undertaken something like 15 years ago at Preston by BNFL? And it's quite simply, although we've closed down our operations, the actual recovering and refining of yellow cake, or U308, if you remember, that still continues in other parts of the world. And I think for the nuclear fuel cycle, it is an essential part of the fuel cycle that prepares the uranium ready to make uranium reactor fuel. So if we didn't present this to you, there would be a fairly big gap in your knowledge base and understanding this fuel cycle, I'll show you in a minute, actually understanding there's various stages of the fuel cycle. So what we're going to be talking about in the next, it may overrun into the next section, but not to worry about that. We'll talk about how we convert this impure, it is not reactor grade, it's slightly impure uranium into a form that it can be used to manufacture nuclear fuel. How we then going to enrich, because if you remember from your chemistry presentations, naturally occurring uranium is only about 99.3% U238. U235, which initially is the energy component of nuclear fuel, is 0.71%. We need to increase that for the more modern reactors up to about 3 to 4%, possibly even a little higher to 5%, depending whether it's an AGR or a pressurized water reactor called STOP. We'll briefly touch on, very, very briefly, on Magnox fuel. So you know the difference in how we did make Magnox fuel, but as you know, there are no Magnox power stations operating today. Certainly not in the United Kingdom and nowhere elsewhere on the globe. We'll then talk about how we convert the enriched uranium hexafluoride into oxide powder, and then very briefly, because as you're probably aware from the timetable that Javad has produced for you, there are other people going to talk about nuclear fuel, either in a reactor or its manufacture at Westinghouse, some 4 miles away from where I am sat today. Okay, so this is the nuclear fuel cycle, and this is the part here we're talking about. We've discussed that. the uranium mines and milling and preparation of UOC, for example. And as I indicated earlier, we do not have a commercial uranium mine in this country, full stop. We don't have the uranium deposits in this country. So if someone comes along trying to sell you shares in a uranium Great Britain mine, then you know not to invest because it will be a scam. Okay? Mostly in Canada, Australia. Australia's probably the largest uranium country in the world. Probably Kazakhstan is near to #1. Sometimes it could be #1, but trying to obtain information from that part of the world is still a little bit more difficult, full stop. Canada is certainly in the top 3. Okay, this next PowerPoint presentation, ladies and gentlemen, is indicating to you, it's jumping ahead a little, but it's indicating to you the sort of quantities of uranium that we have to handle to finish up with a reactor material, okay? And obviously, as we spoke a little earlier this afternoon, where the ore body is only 1,000 parts per million, then we're talking about for a 7,000 ton mining operation based on uranium 7,000 tonnes, we're talking about colossal sums of material having to be handled, and therefore the type of equipment needed is certainly not nano size. Okay, but as we again come down through this flow chart, for want of a better description, you will see as the uranium becomes more pure, then the size of equipment needed obviously reduces, and therefore again the environmental impact will reduce as less and less residues, less and less waste are produced. Okay, but it's an indicative slide to tell you that initially we really do start with mammoth quantities of ore body because of the overburden, etc., etc., and we finish up with basically something that weighs about 10 grams, i.e. a pellet. Okay? Let me just move on a couple of more and then, oh, here we are. Right, and again, as we discussed, our chemical engineers would shout at me and frown and say, but this is not a flow sheet, Addy. And they would be right, because at each of these individual stages, as it's telling you here, how we convert the yellow cake into a uranium hexafluoride, there are at these various stages, we would have chemicals, quantities of chemicals going in, effluents and their quantities and constitution coming out. We would have heat balancers, etc., etc. That's what a chemical engineer would call a flow sheet. This is just illustrative, showing you that in the actual conversion of yellow cake to UF6, we use fairly simple, discrete stages. Okay, not that dissimilar to what we talked about uranium mining. We talked about comminution, where we have both jaw crushers, and I didn't mention this, but jaw crushers are mentioned in your notes page. Jaw crushers are there to crush the big chunks of ore body, the things that are probably the size of a conventional gas oven or electric oven, for example, to crush those down into sizes something of resembling a teacup. But that's not small enough. And then you go to rod mills and ball mills, where that teacup size is squashed down or comminuted into sizes of around about 200, 300 microns. So there are discrete stages for these operations. and the actual refining of the UOC is no different. But here we will be talking about more about chemical processes than we talked about previously. Okay, right. So we've now our Canadian ore producer or ore processor has now sent to us a 45-gallon drum, something like 210 litres drum of U308. The Canadians would call it yellow cake. Not quite that vivid yellow, it's a khaki colour rather than yellow. In that 210 litre drum, there would be 300 kilograms of UOC. It's a fairly dense material. The density of uranium metal itself is up in the 20-30 grams per centimetre, cubic centimetre arena, okay? Well, this is a fairly dense, free-flowing, generally free-flowing powder. Again, it will be a particle size a little bit larger than the actual milling of the ore body. But it's probably where we talked about 200 microns for the ore leaching. This is about probably twice that size, might be a little bit more than twice that size. In comparison, it's still fairly small, okay? And this is what first happens. This material having undergone a independent analysis because BNFL did not own the bulk of the uranium that it processed. It was a toll provider. In other words, someone like EDF would buy the uranium from the Canadian Mining Corporation. It would then ask BNFL to convert it into, for example, fuel. So BNFL didn't own a lot of the uranium it processed, and it was capable, as I mentioned earlier, it was capable of processing 10,000 tonnes of uranium. And in this flow sheet, we will always talk about uranium as being the indicative number, okay, or unit, beg your pardon. So it could handle 10,000 tons of uranium. So it's now being sampled to make sure that the mill has recorded and reported the correct quantity and the correct quantity of uranium in that 210 litre drum. And what do we do with it next? We tip it into a dissolver. Excuse me. Remember, ladies and gentlemen, I've said a dissolver. So here we're trying to dissolve all of that UOC. Not leach, dissolve. Okay? And we dissolve that UOC, yellow cake, as our Canadian colleagues call it, with nitric acid, round about 70% nitric acid. Now, back in your chemistry days at A level, if you were allowed to handle nitric acid, a Winchester of nitric acid that comes into your laboratory and you have to wear the appropriate safety equipment, that nitric acid would be far more concentrated than the 70% nitric acid used here. And the 70% actually refers back to what the bottle you receive is something like 16 molar nitric acid in solution. So here we're talking about 12 molar nitric acid concentration. And we dissolve that UOC at a temperature 80 to 90 degrees centigrade, because obviously we'd like a fairly quick throughput. The actual dissolver itself is partitioned into various quarters. And it's very much like, if you remember when we talked about countercurrent processes, this is very similar. The bulk of the nitric acid is added at the fourth quadrant, where the actual uranium content of the yellow cake is going to be very small, because that's where we want the maximum efficiency of the nitric acid to ensure we've got complete dissolution. And those are the equations. There will be very little uranium-4 associated with yellow cake, but there will be some. But in comparison to uranium-6, UO2 2+, very, very small indeed. But bear in mind one thing: nitric acid is a very good oxidizing agent. So it will oxidize the uranium-4 to uranium-6 fairly readily. Okay? Now, when you dissolve most metals and powders in nitric acid, they will evolve oxides of nitrogen, NOx, or oxides of nitrogen. N02 in particular, and if you recall your A-level chemistry, one of the things about N02, it's very visible. It's a very nice brown gas. Well, very nice in inverted commas. The other thing about it, it's very soluble in water. And we'll talk about that in the next slide. But other oxides of nitrogen, NO for example, are also discharged. NO can undergo oxidation by oxygen in the atmosphere fairly slowly to NO2. NO, unfortunately, is not soluble in water. So when it does start to oxidize to NO2, we can remove all of it by contacting with water. But until we've oxidized the NO, which is a colorless gas, unfortunately, it's not soluble in water. Okay? Right, so we've now got the uranium, the UO2 2+, dissolved in nitric acid, and it's dissolved in nitric acid as UO2 NO3 twice. Obviously, the two NO3 minuses have neutralized that UO2 2+, so we now have got a stable molecule that's electronically neutral, for want of a better word. Okay? And this particular PowerPoint slide, ladies and gentlemen, is showing you in the top, or not quite top, but certainly to the left of the slide, it's showing you what the operations were, excuse me, at Springfields. And in my days when I worked at Springfields, it was a chemistry library, for want of a better description. There was a lot of chemistry involved in this operations here. And this particular part of the overhead presentation is showing you what's happening here. We've got dissolution, but not all, although we've talked about dissolving, not all the UOC actually goes into the nitric acid. And therefore, because we're using a liquid-liquid extraction process here, we need to remove all of that insoluble material. And at Springfields, we did so by using what was called a rotary vacuum filter. Why? Because we wanted to make sure we got a very clarified solution of uranyl nitrate stroke nitric acid. Bear in mind at the dissolver stage, we've used something like 70% 12 molar, in inverted commas, it might be a little bit less than 12 molar nitric acid. By the time we've dissolved and by the time it passes through the filter, that nitric acid is down to what the chemists would call about 1.5 molar, about 10% free acidity in that uranyl nitrate solution. Now that's important, as we will explain in a few minutes. So we've now filtered the excuse me, we've now filtered the uranyl nitrate nitric acid solution, and we now want to recover and further purify, because the uranium is still not reactor grade. It still is associated with neutron poisons such as boron, such as cadmium, for example. We need to produce reactor grade uranium before we can make nuclear fuel. And how we do this is by this liquid extraction process, and it's explained in your notes page. That's why liquid extraction is important to the uranium refining. We use this process called tributyl, or this reagent, beg your pardon, called tributyl phosphate, TBP, dissolved in odorless kerosene. Kerosene, if you like, not that different to aviation fuel, but probably not as flammable, because that's important from a health and safety point of view. And we contact the uranyl nitrate, and these are mixer settlers, and we all know about mixer settlers now. We contact that uranyl nitrate solution in a mixer settler with this TBPOK that's immiscible with nitric acid and with water, and that TBP extracts out of the aqueous phase the uranyl nitrate. Uranyl nitrate. It doesn't break down any binding energies between the uranyl ion and the nitrate ion. It extracts uranyl nitrate. Okay. We've now got uranyl nitrate in the solvent phase, roughly around about here. When we're doing the extraction process, the uranium will be there at a concentration around about 350 grams per litre. Okay. When it's extracted into the 20% TBP OK phase, the solvent phase, something like 70 grams per litre will extract into that TBP OK phase. So from a chemical engineer's point of view, he or she will tell you that we need a solvent to aqueous ratio something approaching 4 to 5 to 1 to ensure we can extract all of the uranium out of the aqueous phase. Okay, so on this stage now, we've got uranium round about 70 grams per litre in the solvent phase, the TBPOK. We now need to back extract it. It has to be reversible, otherwise it's no good. No chemical process, unless they're reversible, are, let's say, commercially viable, for want of a better description. So we now contact the loaded TBPOK, loaded with the uranyl nitrate. We now load it with very dilute nitric acid. Bear in mind, at the extraction stage here, it goes into the solvent phase out of something like a 1.5 molar solution. Here, we're back extracting at a slightly higher temperature, up to about, and certainly no more than 70 degrees centigrade. We use something in the region of 0.05 molar nitric acid. So the temperature and the low acidity causes the uranium to back extract out of the solvent phase into the aqueous phase, and we can achieve an aqueous phase uranium concentration of around about 110 grams per litre. Okay? And obviously we've now cleaned up the TBP because it contains no uranium, and we can recycle it. It'd be no good if we have to throw it away. It will be an environmental challenge for us, and it could become expensive. Although TBP itself is probably on the commercial market only sold at something like $5 to $10 per kilogram. It's a fairly cheap reagent. And again, when you're developing new processes, the cost of your reagents can become critical, to say the least. So now here, round about here, we've got a 110 gram per litre uranium solution in very dilute nitric acid. No good to us because it's in solution. We need, think on, we're making a fuel, which is a solid. We need to convert that to a solid. So one way of doing this, first and foremost, we evaporate the solution such that the liquid coming out of the evaporator is in the region of 1,100 grams per litre uranium in virtually very, very small amounts of nitric acid, probably, for want of from a chemist's point of view, insignificant sums of nitric acid. That solution of 1,100 grams per litre of uranium, actually, if you like, in terms of viscosity and density, resembles Tate's treacle. If you can recall your days when probably you were much, much younger, you probably liked treacle sandwiches. I wasn't too keen on them, I must admit, full stop. But it is a very viscous liquid. It has to be kept at 60 degrees centigrade, because if not, it would solidify. And in converting that uranyl, well, we don't convert it at the moment, but we've converted it into a much thicker liquid, or produced a much thicker liquid. And that liquid then passes into this stage here. This stage here is called thermal denitration. And just think about what we're saying there, thermal denitration. And that very viscous liquid here is uranyl nitrate. So what does that phraseology tell us? Denitration. It means we're going to break down that uranyl nitrate. We're going to cleave off the nitrates away from the uranyl, and because it's going to be a fairly strong oxidizing environment, we're still going to retain the uranium at 6+, and all through of this process from here, the uranium has always been in the 6-valent oxidation state. It means that we're going to cleave away the nitrates and produce a material called uranium trioxide, UO3. But the uranium is still in the hexavalent state, okay? And that's what happens. And if we've time after the break, rather than talk about the actual fuel production, because as Javad and I discussed earlier, there are one or two other people who will be talking about manufacturing fuel at Westinghouse. I'll just quickly refer to it, and if I have time, I'll tell you about how we recover those oxides of nitrogen, NOx. Because bear in mind, when we dissolve the UOC, we've got oxides of nitrogen coming out of the dissolver, and we cannot, under the Alkaline Spectra Act, we cannot simply discharge that into the environment, full stop. So now we've got a UO3 solid, which is purified. It contains now reactor grade uranium, which we can now send on for further conversion into intermediate materials ready for oxide manufacture. And the first one we do, in fact, the first process, and bear in mind what I said, all of these processes, from both a chemical, certainly from a chemist's point of view, are fairly simple, from an engineering point of view, the challenges may be a little bit more bigger. We use simple reactions, and we use one-stage units. So the UO3 is initially converted to UO2. Bear in mind what we've done. In converting to UO2, we've changed the oxidation state of the uranium. We've converted it from 6+ down to 4+. On occasions, we said at the milling stage, at the mill and at the mining stage, some of the ore body will contain U4+. Okay? And how do we do that? Well, a very good, cheap reducing agent is hydrogen. And we actually convert the UO3 in a kiln. I think the temperature is round about 300, 400 degrees centigrade. And we convert it with hydrogen in the stainless steel kiln. We've actually activated the UO3 particles with dilute sulfuric acid, and it is dilute sulfuric acid, and a very small amount of sulfuric acid, because it opens the pore structure of the UO3, which allows the hydrogen, obviously, to diffuse in more quickly to convert to UO2. And the U2 is then, the O3 is converted here. The UO2 is then passed through hoppers into a second kiln, and that kiln is an Inconel kiln, not that dissimilar in size and diameter to the hydrogen reduction kiln, but in this second kiln we are contacting the actual UO2 powder with gaseous HF, hydrogen fluoride. And, hydrogen fluoride used to be, not as a gas, but in a liquid form, 37% liquid form, used to be fairly, let's say, regularly present in your university on the benchtop on the shelf. No longer. It is the most dangerous acid you can handle. If you're not appropriately kitted out, even when you are, you can be in jeopardy, but if you're not, then do not handle 30% aqueous HF. Why not? Because it can destroy your bone structure. When I worked in the Sheffield steel industry, I saw a young gentleman who foolhardily decided he wanted to collect his stainless steel sample. He was etching it for metallurgical purposes. He decided because it was near lunchtime, well, it was lunchtime, he couldn't find a pair of tongs to retrieve his sample. He put his hand into this hydrofluoric acid, got hold of his sample, which was about the size of a saucer, quickly washed his hand and his sample, and came for lunch. The next time I saw the young man, he had to have 2 of his fingers amputated, and the actual Sheffield hospital at the time, and I'm now going back to the early mid-1950s, were talking to him about the possibility he might have to have his hand amputated. His fingers had become deformed, and his hand was becoming a liability rather than a attribute. Nowadays, there are antidotes, for want of a better word, for HF burning, but I would never advise anybody to rely on them. Wear the appropriate protective equipment, preferably don't use HF. This is anhydrous HF we're using here. In other words, it's 100%. It's a liquid. It boils at 19 degrees centigrade, And again, once it becomes moist, it has the same impact as, if not greater impact, as a 37% aqueous HF form. So we convert the UO2 to UF4, and of course all of these processes, because they're operating at 350, 400 degrees centigrade, the final product coming out at the end of the rotary kiln is dry. Now, I'm not going to go through this particular overhead, ladies and gentlemen, because this is all about Magnox reactor fuel fabrication. And the reason it's there is because in the old days at Springfields, the UF4 we produced, probably a good 80% was used for Magnox fuel manufacturing. We don't manufacture Magnox fuel at Springfields. We haven't done for the best part of 20, possibly 25 years. Some very interesting chemistry, but it's now in the annals of history. Okay, but if you want to read that slide and the notes pages underneath, it will tell you how we go about making Magnox fuel, which is uranium metal. And again, it's all about oxidation and reduction reactions. The bulk of the HF, beg your pardon, of the UF4 that's produced globally these days will be for uranium hexafluoride production. Right, we'll talk about uranium hexafluoride production, and then we'll have a break. And when we come back, we'll move on to talk about uranium enrichment and its conversion to uranium dioxide, and probably in the last 5 minutes mention fuel fabrication because of other people coming in, and I'm sure they will give you a much better story than I can tell you. But uranium hexafluoride production, this is why UF4 today is prepared. 99% will go for uranium hexafluoride production, and this is UF6. It's an interesting chemical of uranium, or reagent of uranium, in the sense it has a triple point round about 76 degrees centigrade, and the triple point means it can exist as a gaseous, as a liquid and a solid at that temperature and pressure. The reason we prepared it is for uranium-235 enrichment. Because we can easily convert it to a gas, it means we can use gas centrifugation, and previously to gas centrifugation, we could use gaseous diffusion plants, which we'll talk about when we come back after a 5-minute break, if that's comfortable with you, ladies and gentlemen. It is an interesting chemical. There's by far a greater commentary in your notes page. How do we very quickly produce UF6? We react it with fluorine. Fluorine is one of the most reactive oxidizing gases that's known to chemists. We produce it in this particular plant. That was still there some years ago, but not operable, which we will talk about later. And we convert the UF4 into UF6 by reacting with fluorine, and the UF4 is on a calcium fluoride bed. Why do we use a calcium fluoride bed? Because this is a very energy exothermic reaction, and we need to dissipate the heat, and the calcium fluoride bed helps us to dissipate that heat. So coming out of that plant, we will have uranium hexafluoride, which is then poured, inverted commas, into cylinders, 48-inch diameter cylinders, that then go to Capenhurst, or would go to Capenhurst, for enrichment of the uranium-235. Let's have a 5-minute break, if you don't mind, and then we'll pick up on that conversion process after 5 minutes.
I'm going to stop the recording, Harry.